This morning we're going to finish on sliding window flow control and move on to error control, or at least finish flow control today. And we'll say something about the assignment at the end. You know stop and wait flow control, send one packet, stop and wait for an acknowledgement. Sliding window flow control allows us to send W packets, then we have to stop and wait for an acknowledgement. Allows us to send a window size of packets, of frames. Because we now send multiple frames before we wait for an ACK, we need to keep track of which frames we've sent. So we have sequence numbers. Sequence numbers are contained in the header of the data frames. And the acknowledgements. And you can think of the acknowledgements or the receive readies as simply just the header. They contain a number saying what we are acknowledging. Both the sender and receiver keep track of what they've sent and what they've received. So for the sender, we keep track of the frames that we've sent and we've already received an ACK for. That's to the left of here. If we look at it visually, the last frame ACKed is frame 5. Everything before that has been ACKed as well, because we send in sequence, we should receive acknowledgements in sequence. At some point in time, we may have transmitted some frames, but we're still waiting for an ACK, so we keep track of them, frames 6 and 7 in this example. And we're allowed to send up to some maximum window size before we have to wait for an ACK. If we've transmitted 2, and the maximum window size is 7, in this example, then we're allowed to transmit another 5. And that's what the blue rectangle shows in this diagram. So the sender keeps track of some variables that basically tell the sender this information. And similar for the receiver, it keeps track of what it has received and what it has acknowledged. And the receiver has a buffer that handles up to the maximum number of frames. So in this example, 7 frames can be stored in the buffer. If it currently has received 2 frames, then there's space for another 5 frames in the buffer. And as we receive more frames, this window closes. If we receive another 5 frames, then the window will be closed. We cannot receive any more frames, which makes sense because our buffer will be full. What the flow control is trying to do is to make sure that the sender doesn't send too fast to overflow the buffer at the receiver. As we transmit ACKs, or as we remove data from the buffer and transmit ACKs, then we're allowed to receive more. So the window opens on the right-hand side. And just an example that illustrates those concepts at the sender and receiver. If we send 3 frames, then we see what happens with the viewpoints of both the source and the destination. And you can see that they synchronize over time. Of course, they're slightly different at one point in time, but eventually the sender's viewpoint of what has been sent and the receiver's viewpoint of what has been received should be the same. And last week we finished on this example and we considered, okay, what happens if we send another acknowledgement? And in fact, we have 2 types of acknowledgements. In this example, our acknowledgements are called receive readies, saying, I've received some of your data, I'm ready to receive more. And the number here indicates the next sequence number expected to be received. Receive ready, I'm ready to receive sequence number 3. This one, receive ready, I'm ready to receive sequence number 4. There's an alternative frame, acknowledgement style frame, called a receive not ready, RNR, which means I've received some of your data, but I'm not ready to receive any more. That is, my buffer is full. It's acknowledging data that it's received, but indicating to the source it should not send any more. So there's, although not illustrated in this example, there's a receive not ready frame. And we finished on a case, and it wasn't a very good example. Let's try it again. We finished on the case last week of what happens if we send another receive ready. Well, the example I used was not good. Let's try this case. If we send receive ready 7, after all of these steps have been completed, destination B sends receive ready 7. It indicates that I've received all of your frames up until but not including frame 7. The next frame I expect to receive is frame with sequence number 7, which makes sense if it comes after here. We've received 3, 4, 5 and 6. They've been processed, removed from the buffer. Therefore we have space for another 4 frames in the buffer. If we put the 4 into the buffer, process them and remove them from the buffer, then we have space for 4 more frames. So send receive ready 7, and from the destination's perspective, the window size will be what? What's the value of the window size at the destination? After sending this RR7. I've heard 3, I've heard 4. This is the viewpoint of the receiver or destination B before it sends the RR7, the receive ready 7. Then after sending this, what does it look like? It's 7. That is, currently, at this point in time, 3 frames are in the buffer, 4, 5 and 6. 4, 5 and 6. 4 more frames can fit in the buffer. We have maximum space for 7. Then we send receive ready 7, which is acknowledging, saying I've received everything up until 7. The next frame I expect to receive is frame number 7, which implies 4, 5 and 6 have been acknowledged. So 4, 5 and 6 are processed, removed from the buffer, and then we send receive ready 7. Because these 3 have been removed from the buffer, then we can fit another 3 in. So the window size will be 7 frames, the maximum. If we had it graphically, it would go, the blue rectangle would be from 7, 0, 1, 2, 3, 4, 5. This would move and the window would open to the right-hand side. And similar from the source. When they receive this RR7, this is before they receive it, 4, 5 and 6 were outstanding frames, transmitted but not yet act. We receive ready 7, that implies everything before 7 has been acknowledged, which includes 4, which is 4, 5 and 6. So this vertical bar would move along to be between 6 and 7, and the blue rectangle would open up to include 7 frames.
So window size 7.
Window size at the source will also be 7. We can transmit another 7 frames because everything we've sent has been acknowledged at this point in time. If B receives 3, 4, 5 and 6, but they're still in the buffer, it can send a different type of frame. Actually, we'll leave that one there. And sometime later we send frames. I won't. And the receive not ready frame is a special type of acknowledgement which says, I've received everything up until 6, not including 6. I'm not ready to receive any more. This is for flow control saying, do not send me anything yet. I'm still processing what you've sent me previously. So it's an acknowledgement to say that I've received some of your data, but it does not let the source send anymore. So it stops the source from sending. And then if B processes the data and has space available in the buffer, then it may send a receive ready again, saying, now you can send me more. This says, do not send me any more, and then if buffer space becomes available, it would send another acknowledgement, receive ready, please start sending. That's the meaning there.
So I tell the sender that stop.
Stop, yeah. Receiver is not ready to receive anymore.
Why we need the sync to follow INR?
So we can think of this as acting as an acknowledgement. It's acknowledging what we've received up until now, but so it's still informing the source that I've received those frames, but I'm not prepared to receive any more. So it has two meanings. Thank you for the frames that I've received, or that you've sent me, but my buffer is full, do not send me any more.
It's meaning that we have already received.
Yeah, we've received.
But
Yeah.
no more sending.
We've received up until 6, so we've received 5. 4, 5, 4 and 5, for example.
Or up until only 6.
I think in all the cases we consider in this course, an acknowledgement, these are acknowledgements. They don't contain data, they're coming back in response to data. The numbers included indicate the next sequence number expected.
So I think it means that already 5 frames.
Yeah, frame number 5 has been received, 6 has not. 6 is the next one. So that's the basics of sliding window. Before we go through this example, we'll spend some detail on that. Just one more. So there's the receive not ready, some description of that. One more concept is piggybacking. Piggybacking is a concept that's used in a number of protocols, not just sliding window. It's the concept of often we want to send data in both directions, not just from A to B, but also from B to A. And to save some transmission time, we can combine a data frame with an ACK frame. Let's explain that, and then later we'll see the benefits. If we draw a data frame, there's some header and the data. What does a header contain? It contains information needed for the protocol. Most likely it contains a source address, who is sending this frame, destination, sequence number. When we send the data frame, included in the header is the sequence number of that data frame. And maybe other things like the version of the protocol, some checksum. It depends on the specific protocol what's actually in the header. And these take up a certain number of bits or bytes, and that creates the size of our header. And normally the header size is fixed. An acknowledgement, so this is the data frame. And when I say acknowledgement, I mean a receive ready or a receive not ready. We can think of it just as the header. And it normally contains the similar information. Who sent the packet, the frame, the destination. In our acknowledgements, we include an ACK number here. Number 6 is the number being sent back indicating what we expect to receive next. So this is the sequence number. And in the acknowledgement, we indicate what's the next sequence number expected. Let's call that the ACK number. And we may have this other information as well. And let's say the header is 20 bytes, just as an example. And in this case, the ACK size is the same, because we essentially have the same information, except instead of a sequence number, we have an ACK number, and they are the same length. If we have a 5-bit sequence number, then this is 5 bits in length, and so is this. If we are transmitting data in both directions, from A to B and B to A, whether we're using stop and wait, sliding window, any protocol in fact, then we may send some data 0, and we'd send an ACK. If this is data with sequence number 0, this would be ACK with acknowledgement number 1. If at the same time B would like to send data to A, then it can then first transmit the ACK and then transmit a data frame. And then we get the acknowledgement back and so on. So now if we look at data going both directions, what we can do, we notice here B transmits an ACK and then immediately transmits a data frame, because it has two things to send to A: the acknowledgement of the previous data it received, plus some new data, maybe as a response to this or independent of that data received. Piggybacking is combining these two frames into one frame to save some transmission time. This ACK to transmit 20 bytes. The data frame has a header of 20 bytes plus the data. With piggybacking, we can combine the two frames into one. And what we do is, in the header of this data frame that comes back, the data is the data that B wants to send to A. The header contains the sequence number of that data, for example 5, and it also contains the acknowledgement number acknowledging the previous data. So in this example, B sent an ACK with acknowledgement number 1 and a data frame with a sequence number 5. With piggybacking, we combine this information into one frame where the header contains the sequence number 5 for the data being sent and the acknowledgement number 1 for the previous data received. So if I were to draw the packet or the header now, the data frame contains a source, destination, sequence number, version, checksum, and also an acknowledgement number. That is, the header for the data frame contains everything that the original header for the data frame contained, as well as information for that acknowledgement. We basically combine these two together. Because the source and destination of the ACK and the data frame are the same, the source is B, the destination is A. The version of the protocol being used is the same. The checksum simply applied across the header or the header and the data. So we include one more field, which can include the acknowledgement number. And let's say if the acknowledgement number was, this was 1 byte, this was 1 byte, then that would add one more byte to our header. Our header would be 21 bytes instead of 20 bytes. So now we transmit a header with 21 bytes plus the data. Without piggybacking, we transmitted an ACK with 20 bytes, a data frame with a header of 20 bytes plus the data. That is, we transmitted 40 bytes here. By combining the two, we transmit just 21 bytes. We save on transmitting overhead in this case. Effectively, we're reducing the size of the overhead and we can increase the efficiency. So piggybacking is the concept that in some cases, if we're sending data in both directions, we can combine acknowledgements for data that we've received, with data that we want to send back, therefore reducing the overhead of the headers. And to do that, the header of our data frame includes a field for the sequence number as well as the acknowledgement number, making the header slightly larger, but meaning we don't have to send separate frames. We'll see many protocols use this concept. When we look at TCP in detail, it uses piggybacking, or it allows you to use piggybacking. Any questions on that before we go back to the more detailed example of sliding window? Of course, if B has no data to send, it can still send an acknowledgement on its own. You don't have to wait for data to send the ACK. You only piggyback if you have both an ACK to send and some data to send. If you don't have data to send, simply send an ACK on its own. If there's no acknowledgement to send, simply send the data on its own. But if you have both to send, save some transmission time by sending both together as one frame. The last thing we want to do on sliding window is look at how does it improve upon performance compared to stop and wait, and under what conditions. And the example we're going to go through, I have, don't worry, it's not a quiz, some handouts, take one, pass them along. It's just a colour version of what we're going to go through so you can see what's happening with sliding window. It's essentially the answer to this question. In the question we say we're using sliding window protocol. We want to look at, in the best case conditions, for example, if we've got enough buffer space at the receiver, what's the best case efficiency or throughput that we can achieve? We saw with stop and wait, if we remember back, the best case we can do is we send one data frame. If the data frame propagates, assuming no processing delay, we immediately process that data, remove it from the buffer, we send the ACK back, send the next data frame, ACK, and so on. One data frame, ACK, and then this time here is spent waiting for an ACK to come back, and that leads to our inefficiencies in stop and wait if the propagation time is large. We spend all this time not transmitting, therefore our throughput goes down. We want to see what's the best case that we can achieve with sliding window under different conditions. We have a data frame which contains 10,000 bits. Just to keep the numbers simple, has header and data, 9,000 bits of data, 1,000 bit header, total size 10,000 bits, transmission time with a data rate of 100 kilobits per second, the transmission time, and you have the answer in front of you, is 100 milliseconds. 10,000 bits divided by 100 kilobits per second gives us 100 milliseconds. The ACK is just 1,000 bits, so the ACK transmission time is 10 milliseconds. And in the question we state the propagation is 200 milliseconds. So the numbers you have in the handout don't use any units, but use the same values. The propagation is 200, data transmission 100, and ACK transmission is 10. We're going to assume that there's no processing delay, and that when the data is received, the receiver immediately processes it, removes it from the buffer. So in fact, we'll be able to send as fast as possible, as fast as the sliding window mechanism allows us to do. And we want to see what's the maximum throughput or the maximum efficiency we can achieve. In the first example, our maximum window size, let's call it W max, is with a 2-bit sequence number. We can have sequence numbers 0, 1, 2, and 3. The maximum window size we would set at 3. It should be no larger than 3. And in general, with a k-bit sequence number, the maximum window size, 2 to the k minus 1. 4 minus 1 is the maximum window size we should use. Why is it that? And that's a good problem for you to investigate. It's related to if it was larger than that, if it was 2 to the k, or if this was 4, then our sequence numbers wrap around and we can get confusion when we receive acknowledgements coming back. We'll not go through that right now. So in the first case, 2-bit sequence number, maximum number of frames that I can transmit before I have to wait for an ACK is 3. The size of the buffer at the receiver is 3. The receiver can store 3 frames in the buffer, and then the buffer is full and it will not allow the source to send. That's a challenge for you to solve as a quiz or an exam question. If you have 4, you'll find what can happen is that you can transmit frames 0, 1, 2, and 3, and an acknowledgement comes back, and the source A will not know whether the acknowledgement is from, because the sequence numbers may wrap around, is it from the 0 from the or from the 3 from the previous set sent, or the new frame with sequence number 3. Remember, after 3 we come back to 0. If we allow to send 4 frames, frames 0, 1, 2, and 3, the source can be confused. Confusion can occur when it receives acknowledgements, that it doesn't know whether it's acknowledging this frame 0 or this frame 0. That's why we cannot use larger than 3. To see how that works, you should investigate how that, by drawing a diagram like we go through today. You'll see that in past exams it's been a similar question, but I'm not sure if it will be in this year. We'll talk about that later. Let's go through this case. And I won't draw it on the board because we'll go through what you have in front of you. will keep track of what the source can do, the window size of the source. And in blue, we've got the timing of all the, or some of the selected events in here. So initially, from the source's perspective, with a maximum window size of 3, it's allowed to send 3 frames, starting from 0, 1 and 2. So the green boxes indicate frames that are allowed to be sent. The red boxes will indicate frames that have been sent, but not yet acknowledged. So at the start, we may have many frames to send. We're allowed to send 3 frames, 0, 1 and 2. So we start transmitting those frames one at a time. We can only transmit 1 bit at a time and therefore 1 frame at a time. We start transmitting frame 0. Takes 100 milliseconds to transmit, the data transmission time. And then immediately we start transmitting frame 1. Because after transmitting frame 0, frame 0 is moved into the set of frames that have been transmitted but not yet acknowledged. We're still allowed to transmit frames 1 and 2. So we start transmitting frame 1, and when that's finished, 0 and 1 have been transmitted, 2's allowed. Transmit frame 2, 0, 1 and 2 are transmitted. We haven't received any acknowledgements yet. We cannot transmit any more frames. The maximum was 3 before we have to wait for an acknowledgement. So transmit 0, 1 and 2, one after another. Of course, they propagate across the link. Propagation delay of 200 milliseconds. Although it's not shown here, frame 0 will start to be received at time 200. The last bit of frame 0 will be received at time 300. So in effect, the entire frame is received at time 300. B receives the frame, immediately processes the frame, puts it into the buffer, takes it out of the buffer because it's processed and the data is delivered to the higher layer. So sends back an acknowledgement saying, and it's not shown here, receive ready. And the receive ready will contain the acknowledgement number what? This is the data. Receive ready will contain the number 1. We've received frame 0. The next frame I expect to receive is frame 1. We haven't received frame 1 yet. We're about to receive it, but not at the time when we send the acknowledgement. Note we have a full duplex connection. We can receive data at the same time as sending our acknowledgements. So, in fact, what's happening, just after we finish receiving frame 0 and we start to transmit the ACK here, that's what's shown at the small rectangle here, we're also receiving frame 1. But we haven't received it in its entirety. We haven't received all of frame 1 until here. So we send an ACK with an acknowledgement number saying, or including the value 1. The next number I expect to receive is frame number 1. And we have the timing here, 100 plus 200 propagation. Transmit time for the ACK is 10. And another 200 for the ACK to propagate back. That first acknowledgement will be received at time 510. Note, in this example, we are transmitting an ACK for every data frame received. In one of the previous examples, we saw a case where we transmitted an ACK after receiving multiple data frames. It's really a choice of the receiver as to what approach to take. In this case, so it would need to be specified what the receiver does. In this case, always send an ACK when you receive a data frame. Transmitting ACK with acknowledgement number 1, at the same time receiving frame 1. When that's received in full, transmit the acknowledgement for frame 1, which would contain receive ready 2. data 0, data 1 and data 2 were transmitted. ACK or receive ready with the number 1 is transmitted in response to this data frame. The next one will be ACK with acknowledgement number 2 when we receive data frame 1. And the final ACK, or the third one here, receive data frame 2, send an ACK with acknowledgement number 3. ACK 1, ACK 2, ACK 3. Coming back to what the source is doing, it transmitted the first 3 frames. It's now waiting for an acknowledgement. Waiting, 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 receives the first acknowledgement. And because it's received an acknowledgement with ACK number 1, that implies that frame number 0 has been successfully received. Prior to this, frame numbers 0, 1 and 2 have been transmitted. We're waiting for an ACK. If we receive an ACK with acknowledgement number 1, that means that frame number 0 has been successfully received and ACKed. So frame 0 is complete now. We've sent it, we've received an ACK for frame 0. Every time we receive an ACK for one frame, we're allowed to transmit one more frame. So after receiving this ACK, 1 and 2 are outstanding, we're allowed to transmit 3. 0 is finished. We've completed successfully transmitting frame 0. So we immediately transmit frame 3. We were allowed to send frame 3. We transmit frame 3, and after finishing transmitting frame 3, 1, 2 and 3 are outstanding. We're waiting for an ACK for 1, 2 and 3. And we cannot send any more because that's 3 outstanding. As we're transmitting frame 3, at time 610, we'll receive the ACK for frame 1. We see frame 1 was arrived at the destination here. We sent ACK with ACK number 2. It comes back. ACK with ACK number 2 means that frame number 1 has been acknowledged. So now, when we receive this second ACK, 0 and 1 are successful. 2 and 3 are still outstanding. We're allowed to send one more frame, frame 0. We transmit frame 0, after which 2, 3 and 0 are outstanding. When frame 0 is finished, we in fact receive ACK for frame number 2 with ACK number 3. So frame number 2 is acknowledged. 3 and 0 are still outstanding. Frame 1 is allowed to be transmitted. We transmit it. So now 3, 0, 1 are outstanding. Transmitted but not yet ACKed. And that's our maximum. We cannot have any more outstanding. And then, so we receive the 3 ACKs. Of course, these frames are propagating across the link, and eventually acknowledgements for them will come back. When frame 3 arrives at B, B will send an acknowledgement. And if you do the calculations, 100 for transmission, 200 for propagation, 10 for transmission of the ACK, another 200 for propagation. If we started at 510, we'd receive the ACK at 1020. And the same will happen as what happened up here. As we receive an ACK, we can send one more. We'll transmit one more, we'll receive the next ACK, transmit one more, the next, and after sending 3 frames, we'll have to wait again. In fact, it only goes up to another 2 frames. But we can continue 2, 3, 0, we would have some waiting time. 1, 2, 3, some waiting time. 0, 1, 2, and so on. We transmit 3 frames, wait for the ACK of the first frame, transmit another 3 frames, wait for the ACK of the first frame, and so on.
In the sequence, act number will circle or add up 1, 2, 3, 4, 5 or 1, 2, 3, 0, 1, 2, 3.
The ACK numbers acknowledge the data frame received. So in the same way that the sequence numbers of the data frames wrap around, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, the ACK number is simply the next number from the data frame received. This ACK will be 0 because we've received frame 3, the next one is 0. This will be ACK 1 because it's acknowledging frame 0. This would be ACK 2 because it's acknowledging frame 1, and so on. So first 3 ACKs were 1, 2, and 3. These 3 ACKs will be 0, 1, and 2.
And the same, and the RR is 0, 1, 2, 2.
So when I say acknowledgement in this case, I mean a receive ready frame. They mean the same thing in this case. Receive ready, I'm calling it simply an acknowledgement. Different protocols will call it a different thing. So a specific protocol may call it receive ready. It means receive is ready to receive more. It also means I'm acknowledging the data that you've sent me. In general, we think of it as an acknowledgement. So in this example, when I say ACK, it means the same as a receive ready. So it's just a frame with no data, with some fields. One of those fields indicates the number, the acknowledgement number. And in fact, there would be another field that indicates that it's an acknowledgement or a receive ready, the type of frame. Assuming we've got an infinite amount of data to send, this will keep happening. Send 3 frames, wait for an ACK for the first frame, send 3 frames, wait for the ACK, and so on.
In this case, if the propagation delay is very short, it may be sequential.
Okay, we'll see that in the next case. So this behavior, send 3 frames, wait, that depends upon the parameters of the scenario. That is, what is the propagation delay, what is the transmission delay, and what is the maximum window size. To show that, let's look at the next case. Well, first let's calculate the efficiency in this case. If we zoom out from this and draw it over a longer period of time, it would look like this. Transmit 3 frames. When the ACK for the first frame comes back, transmit 0, 1 and 2. When the ACK from the first frame comes back, we can transmit another frame. And when we finish that, the ACK from the second frame will come back, allowing us to transmit another one. Then the ACK for the third frame, allowing us to transmit the third frame. And then we'll have to wait for the ACK of this first frame transmitted. here. So we get this pattern of transmit 3, wait for the ACK of the first frame, transmit another 3, and we could continue doing that forever. Sorry. So we can think of it's happening in phases where each phase is essentially the same. That is, it repeats in all of these cases. Send 3, wait for the first ACK. Send 3, wait for the first ACK, and so on. So we want to know the efficiency or the throughput. So the throughput is the rate at which we receive data. Let's first look, what's the rate at which we're sending data? Every, let's say, time t, within these two blue lines, we're sending 3 frames. T is 510. We calculate on this diagram. If we go to the top at time 0, when we receive the first ACK is time 510. Then we send 3 frames. Another 510 milliseconds later, at 1020, we receive the ACK of this frame 3. So this period here is 510 milliseconds in our example. So every 510 milliseconds we're sending 3 frames. Because all frames arrive, there's no data lost. Every 510 milliseconds we receive 3 frames. And that tells us our throughput. Transmit 3 per 510 milliseconds. On average, we receive 3 frames every 510 milliseconds. Throughput, the rate at which we receive our data. Three frames of data. Each data frame contains 9,000 bits of real data. 1,000 bits of header, 9,000 bits of real data. Every 510 milliseconds. Three frames with 9,000 bits of data each every 510 milliseconds gives us a close to 92.94 kilobits per second. So our throughput is 52.94 kilobits per second. Our data rate of our link was 100 kilobits per second. Quite simply, our efficiency, how efficient we're using the link, is 52.94%. Efficiency is just the data rate divided by the throughput divided by the data rate in this case. I think it's 52.94. It's at the bottom of your, at the bottom of your handout. About 50% efficiency. Why? We send 3 frames and then we have to spend some time waiting, not sending. And that time is about half of the total time transmitting, of the total time before we can transmit more. This is 52% of this. Any questions on how that's calculated? Then the next case, what if we increase our window size? That is, we use a 3-bit sequence number. With a 3-bit sequence number, we can have 8 different values, maximum window size of 7. And that case is shown here. Now we have sequence numbers that go from 0 to 7 and wrap around. Because with a 3-bit sequence number, we can have 8 different values. And our maximum window size is 7. So initially we can send frames 0 through to 6. The green boxes here. Any questions? Yep.
In the first case, we have like 0 to 3 segments, but in the second case, we have 0 to 7 segments.
In the first case, a parameter of the protocol was a 2-bit sequence number. In the second case, the parameter is a 3-bit sequence number. So just 2 different parameters, or 2 different values of this parameter of how many bits in your sequence number. It depends upon the specific protocol. In the first example, we chose 2 bits. In this case, 3 bits. With 2 bits, we can have the values 0, 1, 2, and 3. With 3 bits, 0 through to 7. Just 2 different examples. It's up to the protocol designer to choose the size of the sequence number. So TCP, for example, may have a 16-bit sequence number. Different protocols would define how long the sequence number is. What we're going to show is what's the impact of the length of the sequence number. In this case, with a 3-bit sequence number, we'll see we can transmit our first frame, frame 0. 0 is transmitted. We're waiting for the ACK. We're allowed to transmit 1 through to 6. 1, 2, 3, 4, 5, 6. We're allowed to transmit 7 frames before we have to wait for an ACK. So 0 through to 6. But before we finish transmitting all those 7 frames, we in fact receive an ACK for the first frame at time 510, using the same calculations as before. So the first ACK comes back here. So look closely at this point. Transmitted frames 0 to 4, 5 and 6 are allowed to be transmitted. Another 2. Transmitted 0 to 5, 6 is allowed to be transmitted. But we receive an ACK for frame 0, the first one we sent at the start. Receiving the ACK for this frame allows us to send one more. We transmit frame 6, we're allowed to send frame 7, but at the same time we receive an ACK for the second frame. Frame 1, the ACK comes back, allowing us to send one more. And this keeps happening. We keep receiving ACKs from the previous frames received, with the original frames transmitted, allowing us to continuously send more frames. Transmit 1, receive an ACK. Means when we transmit 1, it reduces the amount we're allowed to send, but as we receive the ACK, it increases the amount. So we see here we're allowed to send 1 and then 2 as we receive the ACK. Transmit 1, we're allowed to send 1. Receive the ACK, allowed to send 2. And that will keep going forever. That is, we're always allowed to send one more frame because we receive the ACK for the first frame before we've finished transmitting our window size of frames. Maximum window is 7. Before we finish transmitting those first 7 frames, we receive an ACK for one of the first frames, allowing us to send one more. As a result, the source is always transmitting forever. We keep receiving ACKs back, always transmitting, no time spent waiting for ACKs, and therefore our efficiency, in this case, if we're always transmitting, then in fact we're always receiving data. The efficiency is just related to what is the header, what is the overhead. We had 9,000 bits of data every frame, 1,000 bits of overhead. Our efficiency is 90%. 90% of the time transmitting real data, 10% of the time receiving real data. So our efficiency is 90%. Our throughput is 90 kilobits per second in this case. And that calculation is at the bottom of your handout. You could calculate over any period of time over, yeah. So the point to notice is that we're always transmitting, no time waiting. So if you look at any period of time, say from 0 up until 510, and you calculate the number of frames, there'll be 5 frames transmitted. 5 times 9,000 divided by 510, and you'll get 90%, or 90 kilobits per second. If you went from 0 up to 700, then you'll calculate 90% or 90 kilobits per second. So you choose any time frame and you'll get the same value of efficiency. Or the easier way to think of it, there's no time spent not transmitting. Always sending data, always receiving data, and therefore the efficiency is simply the amount of time spent receiving the real data. If we're always receiving data frames, then 90% of the time is receiving real data, 10% of the time receiving the header. Efficiency of 90%. And that's the best we can do in this scenario. Assuming we cannot reduce the size of the header, assuming that's fixed, we cannot do any better than this. Increasing our sequence number, originally it was 2 bits, we increased it to 3 bits. We increased our efficiency from 52% up to 90%. If we increase our sequence number to 4 bits, a 4-bit sequence number, maximum window size is 15. We can send 15 frames before we have to wait for an ACK. What's going to happen? It's the same. Except these numbers will be different. It will be 0, 1, 2, 3, 7, 8, 9. But still, we receive the first ACK before we've finished sending the window of frames. We get the same efficiency. We cannot do any better than 90% because we always have this 10% of header. So increasing the window above, or the maximum window above 7 doesn't help in this case. What happens if we have a 1-bit sequence number? What do we call it when we have a 1-bit sequence number? A 1-bit sequence number means the window size is 1. We can transmit 1 frame, then wait for an ACK. 1 frame, wait for an ACK, which is stop and wait. Stop and wait is just a special case of sliding window. Send 1, wait for the ACK. Send 1, wait for the ACK. This is stop and wait. And of course the efficiency will be much lower in this case if we use stop and wait. Okay, any questions on how we... So this is showing, before any questions, this is showing the impact of changing the window size or the number of bits used for the sequence number on the performance or the best case performance of sliding window. Depends upon really three factors: propagation delay, transmission time, and the maximum window size. If we change our propagation delay to be much shorter, 2 milliseconds instead of 200, then you'll see that instead of 52%, we'd get a much higher efficiency because we'd spend less time waiting. If the propagation delay is smaller, then there's less time waiting for the first act to come back and more efficient transmission. So those three factors are the main things that impact upon the performance: window size, propagation delay, transmission delay. Any questions on sliding windows so far?
Window size, propagation delay, and the third is
Transmission delay, data transmission delay. So you should be able to answer a quiz question next quiz. Maybe not calculating all of this in a quiz, in an exam easily, but understanding the trade-offs between the different factors. Understanding what happens if we increase the propagation delay, or what happens if we increase the window size. And of course how the source and receiver keep track of those values.
window size, propagation delay แล้วก็ transmission delay สามารถ
The main factors that impact on performance: the window size, propagation delay, data transmission delay. Of course, the header size does, the ACK size does, but usually they're very small, and therefore they have a very small impact. So in practice these are quite small, so the main factors are these three. So depending upon your link, we cannot change the propagation delay normally. The distance from us to the destination we cannot change. So if we know the distance and know the propagation delay, if we know our data rate, we pay for a link, we know the data rate and we know the data size, we know these two values, therefore we could choose an appropriate value of the window size that gives us the best efficiency. We saw in our scenario, with a specific propagation and transmission delay, a window size of 7 gives us the optimal efficiency. Window size of 3 is around 50% efficient. We would choose 7. A window size of 15 does not help. We still get 90% efficient. The problem of using a larger window is the size of the buffer at the receiver. The receiver needs a buffer to store the window size of frames. So the larger the window size, the larger the buffer needed at the receiver. More memory needed at the receiver. And in some receiving devices that can add to the cost or complexity of that device. Any last questions before I return to the slides? Of course, this case is the best case in that we didn't consider what happens if there's no space available in the buffer, or it takes a long time to process the data, which in real life may happen. That is, we receive the data, it has to be stored in the buffer before it's processed and removed from the buffer. But you could work out what happens in those cases. This is showing the best case performance. And the other thing we assumed here is that we always send an ACK every time we receive the data frame. In fact, in practice, the protocol may be different. It may decide to wait some time before it sends an ACK acknowledging multiple data frames at once. We saw that in our example on the slides. We saw this is an example. The receiver makes a decision. It receives the first frame. Instead of immediately sending an ACK, let's save some transmission time of the ACK and wait for a little bit longer and see if we receive more data. Turns out we receive 3 data frames, and then the receiver decides, okay, I have 3 data frames, nothing has arrived, therefore let's send an ACK for those 3 frames at once. The alternative, receive a data frame, send an ACK. Receive a data frame, send an ACK. Receive a data frame, send an ACK. Both are reasonable alternatives. The problem of sending 3 ACKs is we increase the overhead in the network or the link. We transmit more. The problem of sending 1 ACK, we have to know when to send it. That is, do we wait for 3 frames? Do we wait for 4 frames? How long do we wait before we send the ACK? And that may reduce the efficiency at the source as well. But in general, it's up to the receiver as to when to send the ACK. If I give you a question, I would specify what the receiver does. Sends an ACK every frame, every 2 frames, or every X milliseconds. And that finishes our coverage of sliding window. And in fact, flow control. That's all we want to cover on that. Next topic, error control, but I just remember we've skipped 1 slide. And just in the last 5 minutes, where'd it go? Last 5 minutes. 1 slide we skipped after stop and wait was, how big should a frame be? I've given numbers in different examples, 9,000 bits. What's the best size for a frame? Well, there are different trade-offs. And normally, a protocol will specify at least the maximum size of a frame. What are the trade-offs? Now, in any protocol that we consider, not just the flow control, normally there's a limit of the maximum number of bytes contained in a frame, the maximum amount of data, and normally the header size is defined as well. So a particular protocol will say what is the size of the header and structure of the header, and what's the maximum amount of data. Quite simply, the larger the frame, the less the overhead. Because if I have 1,000,000 bits to send, the larger the frame, the less frames I need to send to transmit that 1,000,000 bits, and therefore the less header I need to transmit. So making the frame large will reduce overheads. That's the advantage of large frames. But the advantage of small frames, there are multiple advantages. we can use smaller buffers at the receiver if we have small frames. If we retransmitting a small frame is better than retransmitting a large frame. And in some protocols, it's useful to allow small frames so that multiple people get an opportunity to transmit. Let's give an example of one or two of them. Let's say I have 10,000 bits of data to send. That's the total amount of data I want to send. I need to divide that into frames. Let's say we have a frame size which has a limit of 1,000 bits of data plus a 20-bit header. So every frame contains a maximum of 1,000 bits of data plus a 20-bit header. How many frames do we need? $10,000 bits. Every frame can have 1,000 bits. We need 10 frames. How much overhead do we have? Every frame has 20 bits, 10 frames, we have 200 bits of overhead. Total amount of header. To send 10,000 bits, we need to send an additional 200 bits of overhead or of headers. Different case. Frame is 100 bits. Same size header. How many frames? 100 frames. 100 frames, 20-bit header, we have 2,000 bits of overhead. So this is the point that larger frames minimize the header overheads. Smaller frames, larger amount of overhead in total to transmit the same amount of data. Now, what happens if we have errors? And although we haven't looked at error control yet, we know the one basic scheme. If we have an error in a frame, then we'll ask the source to retransmit, send again that frame. Let's assume in every 10,000 bits, there's a chance that one bit will be in error. We don't know which bit, but one of those 10,000 bits will be in error. So, if our frame was 1,000 bits of data, we're transmitting 10 frames. How many frames are going to be received in error? No. One frame. That is, if we split this 10,000 bits into 10 frames, one of those bits is going to be in error. Therefore, one frame is going to have an error in it. So there will be, in this case, one frame received in error. And if we receive that in error, then we'd need to retransmit that frame. So we'd need to retransmit, send again one frame, which is retransmitting 1,000 bits. If we have one frame in error, we'd need to resend 1,000 bits, plus the header. In this case, 100 frames, how many frames have an error? One frame, just one bit in error. Only one of those frames will have an error. So we'll have to retransmit that frame. But the frame is smaller. We only need to retransmit 100 bits. So in the case of errors, with a 1000-bit frame, we'd need to send 10 frames of 1000 bits plus header, plus one of them would need to be retransmitted. 1000 bits would need to be retransmitted. In the second case, we send 100 frames of 100 bits plus another retransmitter frame of just 100 bits. We don't have to retransmit as much as this case. This can be better. So with a smaller frame, there's less overhead due to retransmissions if there are errors. So just two trade-offs that need to be considered with the frame size. And there are other factors as well. If we have a fixed size of buffer at the receiver, if our buffer at the receiver was what have we got? If the size of the buffer at the receiver was 5,900 bits, the size of the buffer at the receiver was 5,900 bits. If we're using 1,000-bit frames, we can fit 5 frames in the buffer, 5,000 bits. The 6th frame would not fit. But if we were using 100-bit frames, we could fit 59 frames, or 5,900 bits. With a smaller frame, we can make more efficient use of the buffer at the receiver. So smaller frames allow more efficient use of the buffer at the receiver, or allow us to send more data if we have limited size buffers. So there are trade-offs on what's the best frame or packet size.